This video is all about complex numbers. You might be thinking to yourself that you already know everything there is to know about complex numbers, and that very well may be the case. However, I'm going to present some things a bit differently than you would normally expect from a high school math class that talks about complex numbers. And the reason for that is that there are some far-reaching implications for complex numbers, and in order to fully understand what those are, there's a connection between Euclidean coordinate planes and or Euclidean planes in general, and some analytic geometry, some visual representations of complex numbers that are pretty important when we move forward into the applications. By the end of this video, you should have a solid understanding of complex numbers and understand the different parts of complex number, as well as be able to do a fair amount of algebraic manipulation. So here's my introduction on complex numbers. That's kind of the story. This is a story of math, and because it's a math story, it doesn't take place on like a timeline. It takes place on a number line. So when we're 1 to 2 years old, we learn about natural numbers like 1, 2. So I'm just going to draw a number line here. Here's a number line. This is maybe 1, 2, and 3. Okay, so there's a number line, and then later on in second grade, we learn about whole numbers, and really the only addition after the natural numbers when we include whole numbers is 0. Then in third grade or so, and this is all in the United States, in the third grade or so, we learn about rational numbers. So we learn about the numbers that are in between the whole numbers or the natural numbers. And then it's not until the sixth grade that we start to realize that there are negative things. So everything on the right side of the number line is also on the left side of the number line, but kind of like in a negative version. So we'd have -1, -2. And then somewhere in there we have irrational numbers. So we talk about numbers like pi. So like pi's over here, right? 3.14. It has a definite space, definite place on the number line, but cannot be expressed as a ratio of two integers. And since then we learn about complex numbers. But what is a complex number? Well, what if I wanted? You could tell me where any number on this number line is. Realistically, if I asked you to point out where is a million, you'd be like, well, it's way over there, right? But if I asked you to tell me what this number is right here, your first instinct might be to say that this is not a number. It's not on the number line. What are you talking about? Well, in order to quantify what that number is, we have to have some way to say what is up? What is up from the number line? What is going on here? So it might be useful to introduce a vertical axis. So here's this vertical axis. And then if we label this vertical axis, well, what do these labels represent? Like on the horizontal axis, those are numbers. Those are the numbers that we're used to using. But then on the vertical axis, well, what are those? And so maybe what we have to do is think about, how do we move things around mathematically? Like, how do we change fundamentally? How do we change 2 to be -2? And sure, we can subtract 4, but really what we would do is multiply by -1. So multiplying by -1 takes us directly from here to here, and you could think that it kind of does so by rotating 180 degrees. That's not a very good semicircle, but that's what it's supposed to be. And so this 180-degree rotation corresponds to multiplying by -1. So if that's the case, what would a 90-degree rotation be? Well, we can figure that out. So let's say we don't know what it is, right? We don't know what we have to multiply something by in order to rotate it 90 degrees. We don't know what we have to multiply something by in order to rotate it 90 degrees. But we know that if we multiply it by that thing and we multiply it by that thing again, it equals -1. Right? That's what we said. We said a 180-degree rotation, which is two 90-degree rotations, would be just like -1. So then we could say that something squared, because something times something is something squared, is equal to -1. And then if we wanted to basically solve this for that something, we could take the square root of both sides and say that whatever that thing is that we multiply by, it's the square root of -1. Now here you're like, oh, Mr. Gribble, I know that the square root of -1 is just I. And you're right, it is. But just saying that the square root of -1 is equal to I is not a comprehensive understanding of what a complex number is. In fact, that is a complex number, but I is not a complex number. I is simply one imaginary unit, essentially. So this axis, this horizontal axis is the real number line, and this vertical axis is the imaginary number line. You could call it just capital I. And so up we have like I right there. This would be 2I. This would be 3I. And so if I wanted to quantify what that point there was, maybe it's like 1.2, right, in the x direction, in the horizontal direction on the real numbers line, and then plus, I don't know, about 1.5I or so. And so that is that number right there. Why would we go through the trouble of explaining complex numbers in this way? Well, because we can also think about complex numbers in kind of like a vector. And if you don't know what a vector is, don't worry. But thinking of them in this way can allow us to do all sorts of interesting manipulation, and it shows us that they sort of behave in a very similar way to vectors. So we can do all kinds of we can like do all sorts of manipulation with two complex numbers, and they follow predictable patterns. So this is actually really important. And what we can further say is if we started with like 2, right, and we multiplied it by the square root of -1, or I now, and by the way, the letter I is only that because it's short for imaginary, right, imaginary. And we didn't know that the square root of -1 was imaginary. We didn't have a name for it for a while. The first guy to come across it, the first guy to kind of come up with imaginary numbers was this guy named Cardano. He was an Italian mathematician, and this was in the 1500s, and he kind of discovered the need for a complex number or an imaginary number, square root of -1, in the process of solving for higher degree polynomials. It's like there was all this math that we were trying to do, but we couldn't really explain part of it because we didn't have a convention of any kind to deal with this thing, this situation where we had the square root of a negative number. And so Cardano sort of formalized this idea of imaginary numbers, but they weren't called that at the time. It wasn't until about 100 years later when René Descartes, who was the most handsome man in the history of mathematics, he came up with the name imaginary. And he was hesitant to do so because calling something imaginary would imply that it doesn't exist, when it very much does. It's just that you need to use your imagination kind of to understand visually and conceptually what an imaginary number was. And this follows because René Descartes is the father of the Cartesian coordinate plane. He was trying to kind of make this concept fit into this rectangular type of space, of like geometric space, because he was famous for creating the Cartesian coordinate system. Turns out that this plane we're dealing with now, this plane we've drawn on here, is not a Cartesian coordinate plane. It's what's known as a complex plane, also sometimes called an Argand plane, named after a guy named Argand, last name Argand. So why is this useful? Well, like I said, if we multiplied 2 by I, we'd get 2I. If we multiplied 2I by I again, we get -2. So that makes sense because I squared is -1, right? 2 times -1 is -2, and 2 times I squared is -2. Therefore, I squared must be -1. Well, if we went again, I did not draw this scale well. Let's pretend that this is -2I. So multiplying by I 3 times is like multiplying by just -I, right? 2 times -I would be -2I. And then multiplying by I again, I to the 4th, is like just multiplying by 1. So I was equal to the square root of the square root of -1. It's just I. I is just I. I squared is like -1. I cubed is like -I. And I to the 4th is like just +1. Now if I went I to the 5th, if I went again, you can see that this is cyclical. So it's just going to start back over where I to the 5th is the same thing as I to the 6th is the same thing as -1, and so on and so forth. And it follows this pattern. So how can we use that idea to help us when dealing with complex numbers or imaginary numbers that are giving us really high exponents? Well, the truth is that we would never see something like I to the 6th because it simplifies down to something similar or something smaller, right? But if we look at this 6 and we realize that the exponents between 1 and 4, they follow a pattern, well, I to the 5th is just I again. So I to the 6th is just going to be -1. This is just like saying I to the 6 is literally equal to -1. It's the same thing as I squared. Okay, what is I to the 2/16? Well, 2/16 is a bigger number, and if you don't realize like what is divisible by that, something you can do is divide it by 4, right? Is 216, is it divisible by 4? It sure is. And if something is divisible by 4, well, that's going to be back to 1 again, right? If you type I to the 216th in your calculator, 54, right? You will get 1. Okay, so that's just 1. Because there is no remainder, right? The remainder is 0, so that means it's just like as if you multiply by I to, the same thing as I to the 4th. Well, what about 2019? If you took 2019 and divided that by 4, does it go in evenly? No, it doesn't. It's 503, but with the remainder of 3, right? So just like if we had I cubed, and we know that I cubed is just like -I. So I to the 2019 is -I. Go ahead if you want, you can say what would I to the 317 be, right? Can't, like, what would be the remainder there? And go ahead and on your own, and just remember, if you divide that 317 by 4, look at the remainder and then think I to that remainder. What is that? So what is a complex number? Well, a complex number is somewhere on a plane formed by the real number line and this new imaginary number line. It's called a complex plane. Complex numbers consist of real parts and imaginary parts, and we write them out in this standard form of a plus bi, and we'll show you that in a minute, where a is the real part and b is the non-real part or the imaginary part, and together this is a complex number. So you might be thinking, well, what if it had a plus 0i? Well, then there wouldn't be an imaginary part. Is that still a complex number? Yes. If you remember, we've talked about nested number systems before. So we have at the very center, we have natural numbers, the counting numbers, 1, 2, 3, 4. Then we add in 0 for whole numbers, and then we add in negatives for integers, and then we add in rational numbers, which are a ratio of two integers. Then we have irrational numbers, which is kind of outside of that. And then all of that together is known as the real numbers. Well, the complex numbers also include all the real numbers, and these purely imaginary numbers, where there's a 0 real part and a non-zero non-real part. Okay, so it is safe to call every number a complex number, but imaginary numbers are not real numbers. Okay, and obviously real numbers are not imaginary numbers. Okay, so we will learn later also that there's something called the fundamental theorem of algebra, which is a dead giveaway for the presence of complex number solutions to certain types of polynomials. So this is the standard form. Okay, there should never be I to any degree, right? We know I squared can just simplify to -1. We know I cubed can just simplify to -I. We know I to the 4th can just simplify to 1. And it follows that cycle. So you should never have anything other than I to the 1st power. And if you do, it means you're not done simplifying something. So how do you work with complex numbers? Well, there's a really simple strategy, and it's called the Uma-Thurman method, where you pull the I out first. So this is a gross GIF, obviously, and it's not actually called the Uma-Thurman method. I just call it that because the key to dealing with complex numbers is to take the I out first. Let me show you what I mean. So the square root of -50. You can think of this as the square root of -1 times the square root of 50. Well, this is I, so we're going to pull it out and write this as the square root of 50 times I. You can also, sometimes some teachers will prefer you to write I times the square root of 50, and the reason for that is that I is very clearly not underneath the radical sign there. Some students like to write things like the square root of 50, and it's like ambiguous whether that I is underneath the radical or not. So in order to get around that, teachers sometimes prefer to have the I out in front, which is what I will try to remember to do throughout this presentation here. So now what do we do? Well, we just deal with this square root of 50 like we normally would, which is it's the square root of 25 times 2, which was 5 squared, right? So this is just 5i, right? That 5 squared comes out, times the square root of 2. So that is what the square root of -50 simplifies to in simplest radical form. Now, why is it important that we pull the I out first? Well, you might think, based on this rule for radicals, we know that the nth root of AB is the same thing as the nth root of A times the nth root of B. That is only the case, though. There's a stipulation to that rule where A and B are real numbers, okay? And so that's fine, but what we have in here, well, A and B are positive, actually positive real numbers. So what does this mean? Well, what happens here? Well, if we just said that's what happens, negative 50 times the square root of negative 50 times square root of negative 2, well, that's the square root of 100, right? And so 10. But the problem is this is super not equal to 10. If we go and if we actually pull the I out first, right, this would be just like from before. We said that the square root of 50, so we take the I out and we have the square root of 50, and then we take the 2 out and we have the square root of 2. Well, now we have these two can multiply together, so we would have I squared times the square root of 100, which is 10 I squared, and then I squared is negative 1, right? So this is actually equal to negative 10. So this is definitely equal to negative 10. It is definitely not equal to positive 10, and so that's why you have to pull the I out first. So just practice, right? Pull the I out first here. You'll have, like, you can do this on your own, but you'll get the square root of 6. Sometimes we need to multiply two complex numbers together, and this is what that looks like. This follows exactly how you think it would using the advanced distribution property. It is simply distributing binomials together. So we do, however you prefer to do this, but it's 8, so 4 times 2 is 8, minus 4 times 9i is 36i, plus 5i times 2 is plus 10i, and then 5i times negative 9i is going to be negative 45i squared. Look, that I squared right away should be like, that's negative 1. So we have 8 minus 36i, and 10i is negative 26i. And then this negative 45, this is negative 1 here, right? So negative 45 times negative 1 is positive 45. So we end up with 53 minus 26i. We always want to leave it in this form where we write the real component first and the imaginary component second. We also need to rationalize, because when you see an I in a denominator, that is the square root of negative 1, and we can't have radicals in denominators. So when we got rid of radicals before, we know that getting rid of radicals must include multiplying it by that same radical again. And we know about the difference of perfect squares, right? If we had x plus y times x minus y, that's going to get rid of everything except the squared term. So if we square a radical, we're getting rid of it. So that's what we want to do, and these are known as conjugates of each other. So the conjugate of a complex number is when you have just a different sign in the middle. So we need to multiply this by the conjugate, which is 2 minus 4i, 2 minus 4i. Distribute like you normally would. On the top, you're going to end up with 10i minus 20i squared. We know what to do with that I squared. And on the bottom, you'll end up with 4 minus 16i squared, right? Well, you again know what to do with that I squared. So you'd have 4 plus 16 on the bottom. You'd have 10i plus 20 on top. So the answer is going to be 20 plus 10i divided by 20. But then you can go a step further here, obviously, because everything has 10 in it. So we'd be like, okay, it's 1 plus 1, how would we do this? 2 plus I divided by 2. But then you can go even farther, because some teachers will prefer you to separate this out into, if you take basically 2 over 2 plus I over 2, so that's just going to be 1 plus I over 2. And this really, because we're looking for this kind of answer, is the correct answer. Or you could also, technically, you could also say it's 1 plus 1/2 I. Actually, this is probably even more accurate. But note that these are all the same thing. Okay, you can go ahead and do this problem on your own. That's just going to be 1 minus 2/3 I. And same deal here, right? We need to know right away that this negative square root of 16 is really just 4i. So you could also multiply, like you could keep it as square root of negative 16, and we can do you remember, multiply by the conjugate, and you'll end up with, when you rationalize this, 1/2 minus I. And then because a complex number by its very nature looks just like a binomial, it's subject to problems that are like the binomial expansion problems. And so from Pascal's triangle, we know that the coefficients of this is going to, coefficients of the product are going to be 1, 3, 3, and 1. And so we can just fill in what's left. We know that it's going to be 2 cubed. Ooh, that's too late. Sorry. We're gonna have 2 cubed, and then 3i to the 0th plus 2 squared times 3i to the first plus 2 to the first times 3i squared plus 2 to the 0th times 3i to the third. And so this is going to be 8. This is going to be 2 times 2 is 4, times 3 is 12, times 3 is 36. So it's going to be 36i, and the I is just to the first power, so we're fine. Plus, this is 3 times 2 times 9. 3 times 2 times 9 is 45, so it's going to be 45, but then I squared, right? Because we have 3i quantity squared. And then, 3 times 2, sorry, 3 times 2 is not 45, it's 54. It's 5 times 9. It's 6 times 9, sorry, 54. 54. Okay, and then the last one, we'd have 2 to the 0th is 1, so 1 times 1 times 27, 27i cubed. And we can deal with this and this, because we know that that's going to be 8 plus 36i, and then 54i squared is minus 54, because I squared is negative 1, and then plus 27 times negative I, right? So it's going to be negative 27i. And now all we have to do is combine these. So 8 minus 54 is negative 46, and then 36i minus 27i is just 9i. So hopefully that is correct. Ha! It is. Oh, sorry, plus 9i, right? Obviously 36i minus 27i. Right, that's complex numbers. I know that might be a more complicated explanation than you are ready for, but this will pay dividends, especially when we start talking about complex numbers, trigonometric, like complex numbers in a polar context. When we start really talking about them in terms of vectors, the operations that you do with complex numbers, and if you can relate visually to those, it's your goal in any application in the future. You'd have to deal with complex numbers. You will understand so much more if you kind of think about right away when you see 2 plus 3i, you're like, oh, that would look something like 1, 2, 1, 2, 3. It's like that right there. It's that number on a complex plane.